All right, crew, we're back and we're going to work on limits and continuity for functions and several variables. Okay, so let's get into that discussion. All right, so let me write the heading. All right, so our limits and continuity for functions of several variables. Okay, so now we got the function x, y, or a function of x and y. Okay, and now we're going to look for the limit of that function, right? What happens as now an ordered pair x and y approach a certain ordered pair, a certain location, and see what we can say about that limit. Okay, and so again, a lot of the work that we say in this process goes back to 28. Okay, our first semester calculus, calc 1, that we took that limit as x approached a of our function f of x is equal to L, right? This meant that we can get our function f of x to be arbitrarily close, right? As close as you want to be to that limit value L by choosing x sufficiently close to a, right? And we have the epsilon delta definition, the epsilon delta proofs for that work as well, right? That we can make the f of x minus L less than epsilon as long as x minus a was less than delta. Okay. That longer process. And this meant when we did this, we talked about it, right? And again, let's go back to continuity. They want to make sure that we're approaching that same value L if with that f of x, if we're approaching x or x is approaching a from the left or x is approaching a from the right, that we're approaching that same value from either side, right? And so that was one of our kind of key discussions, at least I made it key in my work before, is that we need to make sure that the limit from the left matches the limit from the right to give us that value L in order for that limit to exist, okay? And so now in 20A, or 20C, sorry, when we're talking about trying to find this limit, as a point, considering our function of two variables, x and y, at order pair, x and y approach a certain value AB for our function f of xy, that's going to equal to some value L, right? Some z coordinate, right? This means that we can get a function f of xy arbitrarily close to L by choosing that xy, that order pair, close to that order pair AB. Okay? In the longer notation, in the more kind of detailed math language symbols, right? We're kind of saying that if this distance between our point xy and the point we're approaching AB, if that's going to be less than delta, right, the distance between these 2 points, is from some delta, then when we look at the value of our function minus our limit, that's going to be less than epsilon. Okay, so now in our process, all right, if we have our domain space here, if we have our point xy that we're going to be approaching AB, that when we send it through our function, right, and we start to get our surface, then that the points on our surface, right, that those z coordinates will be extremely close together. Okay, and again, I know it's kind of tricky to think about in 3 dimensions, but thinking about that process of what we did in 28 is going to be very similar to our actions here in 20C of these functional multiple variables. Okay, all right, so with that said, then for our limits of functions of several variables, right, instead of just thinking, okay, we're approaching from the left, approaching from the right, we need to make sure that the limit we approach, right, that value we approach is the same for any path we take from our point xy to get to that final value AB, right? So let's look at a generic statement for a moment. Before we get a function involved. But as common practice, right, let's say we were approaching this point, the origin 0, 0, right? For some function, we can fill that in with the next example, okay? So what this idea is, in the xy plane, I'm trying to think about, okay, as I approach that origin 0, 0, what are different ways that my point xy can approach, right? And so this discussion line, right, path 1, right, we can go along that x-axis. I can take these different points and head towards the origin along the x-axis. Okay, let me get that mouse cursor out of the way. So in this case, y is equal to 0 always there. But x can be any value, right? Another path, we can go along the y-axis, right? Where x is always equal to 0, right? So I can take any point up here and have it get closer and closer to the origin. Any point down here, right? X is going to be 0, but any of those points, I can follow that path heading towards 0, right? And we can do a third path even. There's infinite many paths we can do, right? Along the line y equals x, right? So again, take any point, we can take that point and make it inch its way closer and closer to our fixed point 0, 0. And again, this gives a relationship. The y is always equal to x along that path. So when I start to think about, okay, what points are on that path, points where x and y are the same. 1, 1, 1 half, 1 half, 1 fourth, 1 fourth, so on, kind of thinking about those numerically. Okay. So we can start to work there. And we can even shift this point other locations. And it's a matter of imagining different paths that we can follow. Maybe you want to do a parabola. That would work too, y equals x squared. Okay. But no matter what path I choose, that limit, the value, the z result that we get has to be the same. Okay. So in this case, what the kind of comment is that if that limit as xy approaches 0, 0 for a function, right, for path 1, if that doesn't equal the limit as xy approaches 0, 0 for a function along path 2, path 3, whatever it might be, if those don't match, regardless of the path I take, then the limit does not exist. Okay, but if we keep on getting the same result, when I plug this in, I get, that z equals 2. I go on this path, z equals 2 again. I go on the third path, z equals 2. I just keep on getting the same result for that function, no matter what path I'm taking, no matter what type of points I'm plugging in to get closer and closer to 0, 0, then the limit exists, and we're getting, of course, that common value. All right. So let's take a look at this process, right? Again, thinking about if I was to do it from the left side, the right side, and I'm getting different values with those piecewise defined functions, right? If I'm not getting them to link up, then jump discontinuity, right? That limit doesn't exist. All right. So let's take an example, though, and think about using these different pathways. All right, so let's evaluate the limit. If the limit exists. Okay, and just borrowing one from the book even. Let's take this one, this problem. Let's look at number 12. Okay, and this is on page 950. Taking a limit as xy approaches 1, 0, right? So pay attention to how we're approaching or what we're approaching. And then our function xy minus y, x minus 1 squared plus y squared. So I'm not necessarily worried about what my function is doing at the moment, right? We could graph it. We can plug that into like one of our online graphers and see what that shape looks like. Okay. But here, let's focus on this part. We're approaching 1, 0 for this expression, for this function. Okay. And so off to the side here, if now I'm approaching, right, there's my A, B, x is 1, y is 0. There we go. Make sure I get my point in the right location, right? There's my point we're approaching in my xy plane in the domain for my function here. So one path we can deal with, like I did before, right? For path 1, we can go along the x-axis, right? And along that x-axis, y is equal to 0, and x can be anything, right? X is just equal to x. So when I think about dealing with that limit then, with that consideration of this first path, I'm going to replace that relationship, those quantities I know, for my x and my y. Okay? So along this path, x was equal to x, but y was 0. Okay? So wherever I see that y, I'm placing the 0. X's can stay the same. All right, x is still x, minus 1 is quantity squared, but the y is 0. And when we compute, x times 0, 0, minus 0, so that's 0 in the numerator. X minus 1 squared still here, plus 0 squared goes away, right? And so again, as long as I'm approaching, I'm not actually letting x equal 1 along this path, right? These are all these points where we're defined. 0 over number, that's just going to be 0. Okay, so that's what we get for this first path. But now we see, is this going to work for other paths, right? So for a second path, I'm going to go this route. Okay, and again, we can do a lot of different variations. But let's say this next path, we're going to go along that vertical line where x equals 1, right? So exactly, x is equal to 1 everywhere, y is equal to y, right? It can be anything. So when we start to look at that limit again, what's this become? It becomes this limit as xy approaches 1, 0. And now let's substitute, right? So now in this case, x is always going to be 1, but y stays y. All right. And so similar to what we saw in that first part, we're getting 0, 0 squared plus y squared. Well, that's going to be equal to 0 as well. All right. So it starts to look like, well, those two matched up. So maybe I'm good to say that that's always going to be equal. But now this is where some of these more interesting paths can show up. Okay. And so we have to kind of be a little bit more creative, inventive, or troublesome, however you want to view it. And let's try another. Okay, so there's that point I'm approaching, 1, 0. We can approach that in a multitude of ways, right? But now let's say for this third path, let's say I want to approach along this line. Right, a simple line where this is the line y is equal to negative x plus 1. And again, you can make sure that 1, 0 satisfies that line. So this is going to be our path number 3. Along the line, y equals negative x plus 1, right? So that's going to give us exactly how we're going to substitute. That's what y needs to be equal to. So down here, shifting this up, taking this limit as xy approaches 1, 0, xy minus y x minus 1 squared plus y squared. Let's take our time algebraically. To substitute, x is going to stay, but now y, negative x plus 1 minus y, negative x plus 1, x minus 1 squared plus negative x plus 1 squared, right? So along that line, the y is equal to negative x plus 1. So replacing that relationship in, x can be anything. Now starting to compute, negative x squared plus x minus 1, x squared minus 2x plus 1 plus x squared minus 2x plus 1, right? So foiling out those two. Negative x squared plus 2x minus 1, 2x squared minus 4x plus 2, combining my like terms. Up here, factor out a negative, x squared minus 2x plus 1. I know I'm being a little bit tedious here, but just to take my time, right? We can factor that further as x minus 1 squared, x minus 1 squared, or even at this stage, we can see that these two cancel out. And notice what we're left with, a negative 1/2. So now we've created a different path, still approaching that same point, but we've gotten a different result for our limit. Those other two, we got 0. So with just that one kind of counter example, that one that doesn't work, then we can say that limit as xy approaches 1, 0, for that expression, xy minus y over x minus 1 squared plus y squared, that limit does not exist. And again, it's a tedious process when we start these out, trying to figure, okay, all these different pathways that would work. All right, our hope is that if we start with those kind of more simple paths, letting x, y be a fixed constant, be 0, be 1, whatever it might be, that those limits might differ to get it that it doesn't exist, right? Then we have to start to bring in some of these other expressions, okay, to see if those continue to match up, or if we get one different, then that limit doesn't exist. All right. And so then with that process of taking that limit, finding out where we're going to be, okay, then we start to build up to that continuity, extending it directly from our work with 28. Okay, so for continuity, we're going to extend our definition, our identification from Math 28 or our Calc 1. Okay, skip that down, sorry. Right, and so from Calc 1, from our 28, we're going to be continuous at x equals a if the limit as x approached a for our function was actually equal to f of a, right? And it left us, or identified three things. F of a is defined. We can actually compute a value of the function by plugging a in. We're not getting 0 in denominator, negative or square root, that the limit of our function exists, right? So that's what work we had just completed talking about for multivariate functions, that no matter which direction, what path we're on, we're approaching the same value. And then lastly, that limit indeed matches the value of the function, right? Matches values here. Right, that's what we did back in Math 20A, first semester calculus. So now in 20C, our multivariable calculus, we're going to be continuous at that point, AB, if the limit as xy approaches AB, that point, for our function f of xy, that's equal to f of a b. Right? So again, those three comments that our function is actually defined, we can compute, take that x and y value, plug it into our function, get a real number result. That the limit, and that's going to be the time-consuming part, xy, approaches AB, that limit exists no matter what path we're on, we get the same value. And then lastly, that the limit indeed matches the value of the function. Right? That our results, our values match. And then we're going to be able to say that function continues, that surface continues. We're not going to have any holes, any gaps, any jumps in that surface. It's going to be that nice, what we kind of call smooth surface to track and follow. Okay. I'll leave it at that. Let you read the text and go through. Just building up our way so that we can get into our more thoughtful discussions with derivatives, integrals, with these functional multivariables coming up. Okay. All right. Questions, concerns, let me know. Otherwise, talk to you more soon.